Okay, we're going to continue with our beam analysis. This is going to be our PowerPoint part 2. And you should have already watched the part 1 and taken notes and glued this page of notes into your notebook. You should also have gotten the steps for beam analysis, and this is the steps we're going to be using to work each of these problems. It's kind of like the last thing we did, where there's a lot of steps involved, but none of the steps are hard. You just need to do all the steps. So here's the first problem we're going to do. It is a simple beam with a pinned support on one end and a roller support on the other. We have a single point load right here that's 1,000 pounds, and it's 8 foot from this end and 12 foot from this end. So step 1, draw the problem given. So pause the video, copy this problem down. Okay. Step 2 is redraw the beam and replace the supports with the reaction forces. Well, that is exactly what we had over here. Our pin support we're going to replace with a vertical and horizontal, and our roller we're going to replace with just a vertical. So I've done that on my problem here. And the only one I haven't drawn in is the AX. And we talked about this in the first part of the video, but I'll remind you of why that one is going to be 0. So this is step 2, redraw it, replacing it with the reaction forces at the joints. The other part of part 2 is replacing a uniform load with a point load, but we don't have any uniform load here, so we're good for that. Now we're going to come over to the side and find the reaction forces using the sum of the forces equals 0 and the sum of the moments equals 0. So I'm going to start with the sum of the forces in the x direction equals 0. So we're looking for anything happening horizontally. Well, in this case, the only thing happening horizontally is AX. So AX equals 0. So this reaction force right here is just going to be 0. This is going to be true for all our problems unless we had some kind of horizontal forces acting. I'm also going to do the sum of the forces in the y direction equals 0. And we're going to use a standard XY coordinate system where this direction for x is positive, this direction is negative, for y, up is positive, and down is negative. So my AY is going up, so that's going in the positive direction. So AY is positive going up. BY is going up, and that's going to be positive. And then 1,000 is going down, so that's going to be negative. So I did a sum of all of my forces in the vertical direction, and those should add up to 0. Well, if I add this part to the other side using algebra, I get AY plus BY equals 1,000. Now, if you remember from Algebra 1, one equation, 2 unknowns, I can't solve for that. So I'm going to come farther down. I'm going to skip some space. And I want to leave some space because I'm going to have to come back to this. And I'm going to do the sum of the moments equals 0. So we need to speak a minute about moments. Moments, we said, were force times distance. We said that in our first part of this video. And something else you need to know is that we consider counterclockwise moments to be positive. So what I like to do is whenever I have one of these problems, I just write that right above it, which reminds me that anything going in the counterclockwise direction is going to be positive. So a moment is where something is bending. So I have to decide where my pivot point is. I always put it where my pin joint was. That just seems to make it the easiest. So I'm going to pin it right here. So I'm going to do the sum of the moments at A. So the sum of the moments at A. So in this case, AY has 0 distance away from where I'm pinning it. So its moment there is going to be 0. It also should kind of make sense if I'm holding it down right here and then I push right there, that's not going to cause this to turn. So we don't worry about the one where we're holding it down. The first one that's going to cause a turn is this 1,000 pounds right here. If I push down right here, like this, it's going to cause this to swing this direction. So I've got my force is 1,000, and my horizontal distance there is 8 foot. And if I push this way, like this, that's going to cause this one to go this direction, which makes it a negative. So I'm going to put a negative on it. My next force that's going to make a difference is my By. It's pushing up, so I have a force of By, a distance of 20. And if I push up here, it's going to cause this one to rotate this direction. That makes that one a positive. Okay, that's all my moments, so that's going to be, the sum of that is going to be 0. Now I'm just going to use some algebra here. 1,000 times 8, that's negative 8,000, plus 20 By equals 0. Now this is just a regular Algebra 1 problem. Plus 8,000, 20 By equals 8,000, By equals, divide both sides by 20, By equals 400 pounds. So I'm going to put this in two places. One, I'm going to put it on my diagram here. I know By is 400 pounds. And then I'm also going to take this and plug it in up here for By. So when I do that, I get Ay plus 400 equals 1,000. Now I've got one equation, one variable, so I can minus the 400. And I get Ay equals 600 pounds. And I can put it over here. I'm going to go through and put a little box around each of my answers so I can find them if I need to later go back and look at them. Okay, so this is part 3. Find the reaction forces, and part 4, write the reaction forces on the sketches. I did that. Now part 5 is draw and label the shear diagram. So what you want to do is directly below, here's my diagram I'm working from, and directly below it I'm going to draw my shear and moment diagrams. I've got my vertical axis and my horizontal axis. I've also come through, I put my vertical axis right in line with the end of this one, and I've also come through and put a little dashed line where this force is and where this reaction force is. Those are going to help me out when I'm doing my next sketching. So for the shear diagram, we're talking about linear forces. So what you do is you start on this end and you say, what linear force is acting on it right here? Well, I have a linear force of 600 pounds going up. So from my central axis here for shear, I go up 600 pounds, and that's where my diagram is going to start. And I work across my beam this way, and I say, well, what force does it still feel here? Well, right here, it's still only feeling this reaction force going up. Right here, still only this one force going up. Only this force going up, only this force going up, all the way till I get to this point. So my shear diagram is straight across like that. Now I have this force going straight down by 1,000. Well, if I go down this much, that's 600 down, and I want to go 1,000 down. So from there, I'm going to go this drop from here to here is the 1,000 pounds that I had right there. Now going across here, it's steady all the way till I get to the end here. And at this point, I have a force of 400 going back up. So this distance right here is 400. I should start and end with my two reaction forces. That's the shear diagram. That's all there is to it. Now we're going to do the moment diagram. That's part 6. Draw the moment diagram. The moment diagram is always going to be 0 at the ends. So I know I'm going to be 0 here, and I'm going to be 0 at this end. If I have a point load, I'm going to have a linear moment diagram. And it's going to go up and then linear down. I'll show you what happens with a uniform load in a minute. So what it's going to do is it's going to go from here up to where this point load happens, and then it's going to come back down. Now, how high this point is what we're going to do when we calculate the maximum moment. And to calculate the maximum moment, it's the area under the shear curve. This actually works out to be a little calculus, which many of you maybe haven't had calculus yet, but that's why we calculate the area under the shear curve. So I'm going to look at the area under the shear curve under 1/2 of it. So I'm going to look at this area right here. Max moment. Well, the area under this, it's a rectangle, so it's just length times width. Well, the length of this is in feet. That's 8 feet. And the height of it is the 600 pounds. 8 feet times 600 pounds is 4,800 foot-pounds. Now you might ask, well, how did I know I needed to use this side and not that side? Well, let's calculate it for this side over here and see what we get. So we're going to calculate this one. This one happens to be 12 foot long, and its height is 400 pounds. And look, we still get 4,800. So the answer here is it doesn't matter which side I calculate, I'm going to get the same answer. We'll see on another problem where it's easier to do one side than the other. So my max moment, this height right here, and we write that as M max for max moment, is equal to 4,800 foot-pounds. All right, that's all there is to this. Thanks for watching.